Hello and welcome to part 5 of the motorized helicopter tail series. Today we are in Sasha's workshop. So this is the place where we started with the C7ber project. And today we're gonna talk about this helicopter. We talk about the ESC setup and the RF setup that you need to do this. And we will see an expert level pilot's flight of this helicopter. Yeah. About this one, this was an idea back in 2019, and the basic approach was combining these very compact and robust Kraken gears with a very light carbon fiber tube to get a nice and compact helicopter. Yeah, you don't need to like it, but this was our way to do it. And yeah, it's still with the SAB head, and yeah, it has some very unique thing that does help, especially with this electric tail. This tube here. This is a very unique tube. It's a 0.6 millimeter, and it's made. Yeah, it's like baked in the oven and. Really high quality. There's only one guy in the world who is doing this, and this is very light. This is 80 grams for the tube, 80 grams. So I think most of the helicopters have at least double the weight. So 160 grams, 200 grams. Maybe you will find some with 140, but usually at least double. So this is overall, I think, about 260 grams with blades, with the tail fin, the rod, the belt. So it's really very light. And because of this, we were able to make the helicopter very short and very compact, dense of the components. So why this? Because I personally didn't like to fly to fly with canopy. And so the T-Rexes and everything. I really much enjoyed flying without canopy. I don't know why. I think it's because of the size. And it makes the helicopter more chubby, more longer nose, more heavier and more air resistance. So the idea was, what if we can create a helicopter that has a canopy but does not feel like having a canopy? And so, as you see, the canopy is very, very small. If you compare it to, for example, to this Kraken here, you will see it's a lot shorter, and this can only be achieved with this very light tail, because otherwise you will get in trouble with the center of gravity. And the advantage of this is especially because if you use an electric tail, you're doing your left rudder by pushing the rotor, and this will get more difficult the heavier the tail is, or you will need more energy. You will need a heavier peak on the main rotor. So it's definitely an advantage. That's why we're doing this now with this helicopter. So let's talk about the components used. First of all, the tail motor. This is a T-motor anti-gravity 6007 with 320 kV. And the prop is a 13-inch by 6.5 inches Xoar electric. It's very light. It only has 13 grams or so. It's important to have a light prop, and also to have some kind of bigger prop than compared to the original tail. You can see the wiring. It's going in there. The motor cables came out here, and we have a separate path for the tail wires now into the ESC box. And you can see here the tail ESC attached to the side. This is a Sequre 12100, and the main motor ESC is a 14200 Pro, also from Sequre. They are so small we can put it both in there, and so because some guys ask, it's all running on 12S. So the tail is on 12S and the main motor is on 12S. Maybe 14 in the future, we will see. And we're using this US8 connector, combining all wires together and having anti-spark. But I think it's not necessary to have anti-spark. Whatever, yeah. It's always important to lengthen the motor wires, not the input wires. We did try both. It also doesn't matter about if the tail wires are longer or shorter. Never mind, it works. These are the ESCs we are using. Thank you for Sequre to sending us these. And you can see the 14200 Pro for the main motor and the 12100 for the tail. The 12200 Pro is coming already pre-soldered with wires, and it has a BEC. You can adjust from 6, 7.4, 8.4 and 12 volts. You got the 15 amps continuous current and 35 amps maximum. The wiring, you can see here, this is the signal and you have the voltage for your flight controller. Here you have also voltage supply, and this is the RPM signal. And this is telemetry, D-shot. I'm using D-shot, bidirectional D-shot. You can do the same here with the TX and put these two together on one channel to get the telemetry of both. In the helicopter we mounted it in this position. Actually quite nice because it doesn't need much space. You can attach the fans. I didn't do it because I think it's already enough cooling, and in the telemetry in the video later you can see it's not that hot. Now we set up the ESCs. For this we're using the AM32 configurator, and you can access it online by using the am32.com. You're gonna need the USB tool to connect your ESC to the computer, and yes, you can see this is version 2.19. It's in 3D mode. That's important to get the reversing direction for the bidirectional motor. I'm using D-shot, I'm using complementary PWM. This is the braking of the motor. I'm using auto timing, and the PWM is by RPM. Important to set your motor right. This is 28 poles for this motor. The startup power can be set to 150% to get a quicker startup, and the motor kV is 300. Very important setting. Get your kV right, whatever you're using, otherwise you might fry your motor. The ramp up rate is also quite important. You can also fry your motor if it's too high. I tested from 1 to 16%, so 16 was still fine. The biggest jump was between 1 and 2, and yeah, this is okay. So the minimum duty cycle is, I figured out this 5% is quite the best, so I leave it, and I disabled my current and temperature limit. The main rotor settings are different from the tail. We don't use the 3D mode, and I'm also using the auto timing advance, same as I used with the tail. This works fine for me, so I'm gonna keep it. And yeah, it's important also here to get your motor poles correct, and I'm using PWM by RPM. You could also fix your PWM to 16 kHz. Motor kV and starter power, you can, the kV should be according to your motor. The ramp up rate, I'm using 3%. I didn't test a higher value so far. For a normal tail, not an electric tail, 1% is fine. You're gonna run your motor a bit cooler with it, but if you have an electric tail and using TTA, 3% was okay. The minimum duty cycle 0.5 to have a slow spin up or low initial kick. Temperature and current limits are disabled. You're just gonna save your settings and you're good to go. Now we will do the necessary configuration to change the variable pitch tail to a motorized direction. In the Rotorflight configurator, go to the Mixers tab and change variable pitch direction. It gives us a warning. It's experimental and we have to do additional settings in the CLI. I'm gonna save this. In the Motors tab, you can see you don't have a motor 2. And in the Servos tab, you can see you still have the tail servo as servo 4. So this has to be changed in the CLI. We check our resources. And you can see there is motor 2 is missing and servo 4 is still there. We will attach the output CO9 of servo 4 to the motor 2. So this frees the servo 4. This attaches it to the output. Then we have to set motor control mode to bidirectional by doing, this is the main motor, this is the tail motor, by changing the value for the tail motor to 1. Save it. Check our Motors tab. So we have a motor 2, fine. Check our Servos tab, we don't have any servo 4. That's also fine. So regarding the motors, I'm using DShot 600. I'm using BL Heli 32 protocol, as this gives me the opportunity to use both telemetries, and I'm getting here. So I'm also using DShot RPM telemetry to get the RPM from the DShot for both motors. The tail gear ratio is now set to 1:1 because you don't have any gears. For the profiles, the main difference in the PIDs is that you will have to set your derivative about as the same to your proportional, or in my case, as I'm having a very light tail, I'm doing a little bit more. And you also might change your stop gains for counterclockwise and clockwise. Actually, I'm noticing I might have this reversed. I have to check it. Yeah, just play with these values, and you're gonna use your TTA, your torque assist for the main rotor, in order to get left yaw authority. The first is the gain. Second is the TTA limit. So this does give us how much the motor, the main rotor, is allowed to speed up by this. Okay, one more thing. There is one more thing you could consider in your rates. So you're gonna change your response time to smooth your stick input, because this might help, especially if the tail is heavier. You can also do it in your radio. Now you know the secrets how to do it. You can do it for yourself, but just be aware that it's still in an early stage of concept, and it's working well. It's not as good as a traditional tail, but it might be in the future. And there are still many things to improve. So we can improve the algorithm of the flight controller. We can improve the ESC. So if we use FOC control, would be a huge improvement. We can do some thrust linearization. We can, I mean, there might be new motors in the future, some kind of axial flux things, whatever. The motor might be also way too big. We also will try, so we need to try different motors, so this is not, it might not be the only working setup. Yeah. We will also eliminate the one-way bearing and see if we can reduce the amount of reversals being necessary. I couldn't get a good results with an unidirectional approach. So this means the motor just is turning in one direction. As long as you have the one-way bearing, you won't be able to do it. You definitely need to remove it and see if then there are still some flight conditions you need to have the motor reversed. We will see, we will find out. And yeah. And also, if you see the video, just notice the flight video. There is some strange whining noise. This is the gear. This is not the tail, it's the gear, because this is the very first gear of the Kraken. In 2019 we have straight tooth. And if you remove the tail drive, that's what we did here, then you will get this kind of whining noises. I don't know why. I'm gonna fix it. I'll change it to the slanted version, and yeah. Let's enjoy the flight and see you soon.